For 13 billion years, light has been traveling toward Earth from the edge of everything. Tonight, that ancient light reaches your eyes. What it reveals should terrify and inspire you in equal measure. We thought we understood the cosmic scale. Then the James Webb Space Telescope looked deeper than ever before and found galaxies that shouldn't exist. Massive, mature galaxies in what should have been the universe's infancy. These observations are forcing cosmologists to reconsider everything. But here's the truly unsettling part. Every boundary we discover is on an edge. It's just another horizon hiding something beyond. The observable universe? That's just our local neighborhood. Cosmic inflation suggests reality extends impossibly farther. Quantum mechanics hints at infinite parallel universes branching at every moment. String theory predicts 10 or 500 possible universes with different physics. The question isn't just, how big is the universe? It's, what lies beyond what we can ever observe? And that answer will challenge your entire understanding of existence, reality, and what it means to be conscious in an incomprehensibly vast cosmos. Chapter 1. Observable limits. When you look at the night sky, you're not seeing the universe as it is right now. You're looking backward through time, watching ancient light that's been traveling through space for thousands, millions, or even billions of years. Every photon that hits your eye is a messenger from the past, and the farthest messengers have been traveling since before Earth even existed. But there's a hard boundary to how far we can see, and it's not where most people think it is. The observable universe has a radius of approximately 46.5 billion light-years in every direction. Wait, let me address the confusion you're probably feeling right now. If the universe is only 13.8 billion years old, how can we see objects 46.5 billion light-years away? Shouldn't the edge of visibility be 13.8 billion light-years, since that's how far light has had time to travel? This apparent paradox reveals something profound about the nature of space itself. Light from the edge of the observable universe has indeed been traveling for 13.8 billion years, essentially since the Big Bang. But during those 13.8 billion years, space itself has been expanding. The galaxy that emitted that light was much closer when the light began its journey. As the photons traveled toward us, space stretched between us and that distant galaxy, carrying it farther away. By the time that ancient light reaches our telescopes, the galaxy that emitted it is now roughly 46.5 billion light-years distant. It's not that the galaxy moved through space faster than light. Nothing does that. Space itself expanded and the galaxy went along for the ride. This expansion creates a cosmic horizon fundamentally different from any horizon on Earth. When you stand on a beach looking at the ocean, the horizon exists because Earth is curved. There's more ocean beyond what you can see. The cosmic horizon exists because there's a boundary to how far light has had time to travel since the beginning of time itself. Beyond approximately 46.5 billion light-years in any direction, there are regions of space whose light simply hasn't reached us yet. Those regions absolutely exist, containing their own galaxies, stars, and potentially even observers looking back toward us. But they're beyond our observational horizon, separated from us not by distance alone, but by the fundamental structure of space-time. The cosmic microwave background, the afterglow of the Big Bang discovered accidentally by Arno Penzias and Robert Wilson in 1964, marks the farthest back in time we can observe with light. This radiation, now detected as faint microwaves uniformly filling all of space, was emitted about 380,000 years after the Big Bang, when the universe finally cooled enough for atoms to form and photons to travel freely. Before that moment, the universe was opaque, a hot, dense plasma where light couldn't travel more than a tiny distance before being absorbed and re-emitted. The cosmic microwave background is essentially the surface of this fog, representing the earliest epoch we can observe using electromagnetic radiation. To put this in perspective, imagine Earth's entire history compressed into a single day. Modern humans would appear in the last second before midnight. The dinosaurs would emerge about 15 minutes before midnight. Complex life would begin around 5 p.m. And the cosmic microwave background, our view of the infant universe, would correspond to images from about 2 seconds after midnight, just moments after our day began. Everything before that 2-second mark is hidden behind a wall of plasma we cannot see through with any form of light. But here's where things become even more remarkable. This observable boundary isn't fixed. Right now, at this very moment, the observable universe is getting larger. Not because space is expanding, though it is, but because light from more distant regions is having time to reach us. Every second, light that has been traveling for 13.8 billion years crosses the threshold into visibility. Galaxies that were beyond our cosmic horizon yesterday are within it today. In a very real sense, we're constantly discovering new parts of the universe that have always existed, simply by waiting for their light to arrive. Modern astronomy has mapped this observable sphere with extraordinary precision. The Planck satellite, launched by the European Space Agency in 2009, measured the cosmic microwave background with unprecedented accuracy, creating a detailed map of the universe as it appeared 380,000 years after the Big Bang. These measurements allow cosmologists to calculate the universe's age, expansion rate, and composition with remarkable precision. We now know that ordinary matter, the stuff that makes up stars, planets, and people, comprises only about 5% of the universe's total content. Dark matter, detectable only through its gravitational effects, makes up roughly 27%. And the remaining 68% consists of dark energy, a mysterious force causing the universe's expansion to accelerate. These percentages matter enormously for understanding cosmic scale. Dark energy's accelerating expansion means that galaxies beyond a certain distance are receding from us faster than light can travel toward us. This creates another boundary, the cosmological event horizon, beyond which we will never be able to see no matter how long we wait. Galaxies just beyond this horizon are essentially frozen at the edge of our visibility, their light redshifted into invisibility as space stretches faster than the light approaches. Over cosmic timescales, as dark energy continues accelerating expansion, our observable universe will actually shrink. Distant galaxies will cross the cosmological event horizon and fade from view, leaving future astronomers in a lonelier cosmos. Consider what this means for your sense of position in space. You stand at the exact center of your observable universe, so does every observer everywhere. An observer in a galaxy 10 billion light-years away has their own observable sphere, extending 46.5 billion light-years in every direction from their location. Most of their observable universe doesn't overlap with ours. They can see vast cosmic regions we'll never observe, while we can see regions forever beyond their sight. The universe has no center, no special location. Every point is equally valid as an observational reference. This boundary, this cosmic horizon defining the observable universe, represents the edge of everything we can potentially measure, map, or interact with using light. It's a sphere of knowledge surrounded by an ocean of mystery. And here's what makes this truly profound. This boundary isn't a property of the universe itself. It's a property of our position in space and time. The universe itself, the full extent of physical reality, almost certainly extends far beyond what we can observe. How far beyond? That question leads us into territory where measurements end and theoretical physics begins. Because the truth is, we don't know if space continues forever, curves back on itself, or terminates at some unimaginable boundary. We don't know if our universe is all that exists or merely one region in something far vaster. But before we can explore what lies beyond the observable boundary, we need to understand exactly how astronomers measure these incomprehensible distances in the first place. The methods they use reveal just how creative and brilliant human beings can be when confronting the infinite. Chapter 2: Cosmic Rulers. Measuring distance across a room is trivial. Measuring distance to the moon requires cleverness. Apollo astronauts left mirrors on the lunar surface that let us bounce laser beams and calculate distance from the round-trip time of light. But measuring distance to objects millions or billions of light-years away seems impossible. You can't stretch a measuring tape across intergalactic space. You can't bounce signals off galaxies and wait for a return echo. Yet astronomers have developed ingeniously clever techniques to measure cosmic distances with stunning precision, building what they call the cosmic distance ladder, a series of methods, each calibrated against the previous, that extends our reach from nearby stars to the edge of the observable universe. The foundation of this ladder starts surprisingly close to home. Stellar parallax, first successfully measured by Friedrich Wilhelm Bessel in 1838, uses Earth's orbit around the Sun as a baseline for cosmic triangulation. As Earth moves from one side of its orbit to the other, a distance of 186 million miles, nearby stars appear to shift position very slightly against the backdrop of more distant stars. By measuring this tiny angular shift, astronomers can calculate distance using simple trigonometry. A star that shifts by 1 arcsecond, 1/3600th of a degree, is defined as being 1 parsec away, equivalent to about 3.26 light-years. The closest star beyond our Sun, Proxima Centauri, shows a parallax of about 0.77 arcseconds, placing it approximately 4.24 light-years distant. Parallax works beautifully for relatively nearby stars, but the angular shifts become impossibly tiny for objects more than a few thousand light-years away. To measure greater distances, astronomers turn to standard candles, objects whose intrinsic brightness is known. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate its distance. It's exactly like knowing the wattage of a light bulb, and then figuring out how far away it is based on how dim it appears. The challenge is finding astronomical objects whose true brightness can be reliably determined. Enter Cepheid variable stars, the workhorses of cosmic distance measurement. These pulsating giants, first studied in detail by Henrietta Swan Leavitt at Harvard College Observatory in the early 1900s, have a remarkable property. Their pulsation period directly correlates with their intrinsic brightness. A Cepheid that pulses over 30 days is intrinsically brighter than one pulsing over 3 days. By timing a Cepheid's pulsation period, astronomers know its true luminosity. By measuring its apparent brightness, they calculate its distance. Cepheids are luminous enough to be spotted in nearby galaxies, extending our measurement reach to about 100 million light-years, far beyond what parallax can achieve. This is how Edwin Hubble revolutionized cosmology in 1924 by identifying Cepheid variables in the Andromeda galaxy and measuring their distances. He proved conclusively that Andromeda lay far beyond the Milky Way. It wasn't a nebula in our galaxy, it was an entirely separate galaxy. One measurement changed the scale of the known universe by millions of light years and revealed that our galaxy was just one among countless others. Cepheids have since measured distances to thousands of galaxies, mapping the local universe with increasing precision. But Cepheids eventually become too faint to detect in very distant galaxies, requiring yet another rung on the distance ladder. Type Ia supernovas, thermonuclear explosions of white dwarf stars that cross a critical mass threshold, serve as the next step. These catastrophic events briefly outshine entire galaxies, making them visible across billions of light-years. More importantly, Type Ia supernovas have a remarkably consistent peak brightness, making them excellent standard candles for cosmic distances. The light curve, how brightness changes over time, can be analyzed to determine the supernova's true luminosity with high precision. In the 1990s, two independent research teams used Type Ia supernovas to measure distances to galaxies billions of light-years away, expecting to determine how much the universe's expansion was slowing down due to gravity. Instead, they discovered something completely unexpected. The expansion is accelerating. Distant supernovas appeared fainter than predicted, meaning they were farther away than calculations suggested. Space itself is stretching faster and faster, driven by the mysterious dark energy mentioned earlier. This discovery, announced in 1998, earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics, and fundamentally altered our understanding of the universe's fate. For the most distant objects, even supernovas become rare and difficult to study. At extreme distances, astronomers turn to redshift, the stretching of light waves due to cosmic expansion. As space expands, light traveling through it gets stretched to longer, redder wavelengths. The amount of redshift directly indicates how much the universe has expanded since that light was emitted, which correlates with distance. Galaxies with redshift values above 7 emitted their light when the universe was less than 1 billion years old, placing them more than 13 billion light-years away in light travel distance, though actual current distance is far greater due to continued expansion. The James Webb Space Telescope, launched in December 2021, has pushed these measurements to unprecedented extremes. In 2022, it detected galaxies with redshifts above 13, corresponding to light emitted just a few 100 million years after the Big Bang. These galaxies appear as they were in the cosmic dawn, when the first stars and galaxies were forming. Their light has been traveling toward us for more than 13.4 billion years, though the galaxies themselves now reside more than 30 billion light-years away due to cosmic expansion during that time. We're seeing infant galaxies that have since evolved into mature systems completely beyond our ability to observe in their current state. Each rung of the cosmic distance ladder must be carefully calibrated against the previous rung. Parallax measurements calibrate Cepheid distances. Cepheids calibrate Type Ia supernova distances. Supernovas calibrate redshift relationships. Any error in one rung propagates up the ladder, which is why cosmologists constantly refine their measurements. The Hubble constant, the rate of cosmic expansion, has been measured at about 67-73 kilometers per second per megaparsec, depending on measurement method. This seemingly small uncertainty represents real disagreement between different measurement techniques, suggesting either systematic errors we haven't identified or new physics we don't yet understand. To put these measurement achievements in perspective, imagine scaling down the observable universe so that Earth is the size of a single bacterium, about 1 micrometer across. On this scale, the Sun would be a marble about a hand's width away. The nearest star would be roughly 50 miles distant. The Milky Way galaxy would span the entire continental United States, and the edge of the observable universe would be about 50 times farther than the actual Moon's orbit around Earth. Astronomers have developed techniques to measure distances across this entire scaled range with impressive precision, using nothing but the light reaching their telescopes. Yet these measurements reveal something profound about the nature of astronomical observation. When we look at the Moon, we see it as it was 1.3 seconds ago. When we look at the Sun, we see it as it was 8.3 minutes ago. When we look at Proxima Centauri, we see it as it was 424 years ago. When we look at the Andromeda Galaxy, we see it as it was 2.5 million years ago, before modern humans existed on Earth. When we look at the most distant galaxies James Webb has detected, we see them as they were more than 13 billion years ago, when the universe was young and the first stars were just beginning to ignite. Your view of the cosmos isn't a snapshot of now. It's a time machine showing you history at every distance. The farther you look, the further back you see. This means the observable universe isn't just a sphere of space, it's a sphere of space-time, a four-dimensional construct where distance and time are inextricably linked. Understanding this relationship is crucial for grasping what it means to ask, how big? The universe is because size and age become the same question at cosmic scales. But these measurements, as impressive as they are, only tell us about the observable universe. They map the sphere of space from which light has had time to reach us. What they cannot tell us, what no measurement can tell us, is what lies beyond that boundary. To explore that question, we need to understand not just how we measure the universe, but what the universe actually is at its most fundamental level. And that requires confronting one of the most profound questions in cosmology. Is the universe infinite, or does it have an edge? Chapter 3. Infinite Question. Does space go on forever? It's one of humanity's oldest questions, debated by philosophers for thousands of years before we had any scientific way to investigate it. The ancient Greeks argued about whether the cosmos had boundaries. Medieval scholars contemplated whether God created an infinite universe or a finite one. Today, armed with general relativity and precision cosmology, we can approach this question scientifically, and the answer is far stranger than either yes, infinite, or no, finite. The observable universe, as we've established, has a definite size, roughly 93 billion light-years in diameter. But that's just our observational horizon, the boundary of what we can see. The actual universe, all of physical reality, could be vastly larger, even infinitely so. Here's the profound part. We might never know for certain. If the universe extends infinitely beyond our observable horizon, no observation we make from within that horizon could prove it. Infinity isn't something you can measure. You can only infer it from the properties of what you can see. General relativity, Einstein's theory describing gravity as the curvature of space-time, allows for three basic geometric possibilities for the universe's overall shape. Imagine you're a two-dimensional creature living on a surface. That surface could be flat, like an infinite plane, extending forever in all directions. It could be positively curved, like the surface of a sphere, finite in size but without edges or boundaries. Or it could be negatively curved like a saddle shape, potentially infinite but curving in a peculiar way. Our three-dimensional universe has analogous possibilities: flat, spherical, or hyperbolic geometry. Measurements of the cosmic microwave background by the Planck satellite indicate that space-time appears to be geometrically flat, or at least extremely close to flat. If space is perfectly flat and extends beyond our observable horizon, it's almost certainly infinite. There's no natural place for it to stop. An infinite flat space contains infinite matter, infinite galaxies, infinite stars, and, by extension, infinite planets. This leads to truly mind-bending implications we'll explore shortly. But first, let's consider the alternatives. If the universe has positive curvature, if it is shaped like the three-dimensional surface of a four-dimensional sphere, then it could be finite yet unbounded. Just as you can travel in any direction on Earth's surface and never encounter an edge, you could theoretically travel in any direction through a positively curved universe and eventually return to your starting point without ever hitting a boundary. The universe would have a definite volume, but no center and no edge. If you could somehow travel faster than light for long enough, you'd circumnavigate the entire cosmos and see the back of your own head in the distance, watching yourself depart billions of years earlier. Current measurements place stringent limits on how much curvature the universe can have. If it's curved rather than flat, that curvature is extremely gentle. The sphere is so large that within our observable region, It appears flat to very high precision. For the universe to curve back on itself within observable scales, measurements would detect this curvature clearly. They don't. Either the universe is truly flat, or the sphere is so enormous that our observable region represents just a tiny patch on its surface, too small to reveal the overall curvature. Imagine trying to determine whether Earth is flat or spherical. By examining a square mile of Kansas, you'd conclude it's pretty flat, even though you'd be wrong about the global geometry. Negative curvature, the hyperbolic case, allows for fascinating possibilities. A negatively curved universe could be either infinite or finite with a complex topology, wrapping back on itself in non-intuitive ways. These multiply-connected topologies are mathematically possible but difficult to distinguish observationally. You could potentially see multiple images of the same distant galaxy in different directions if light has traveled around the universe along different paths, but detecting such patterns in the cosmic background requires precise analysis that hasn't yet yielded definitive results. Let's confront what an infinite universe actually means. If space extends infinitely and contains matter at roughly the same density everywhere, what cosmologists call the cosmological principle, then everything that can happen, has happened, is happening, or will happen infinite times. Somewhere beyond our observable horizon, there's another planet exactly like Earth, with someone exactly like you reading these exact words at this exact moment. Actually, there are infinite such planets with infinite copies of you. This isn't science fiction or philosophical speculation. It's a mathematical consequence of infinity combined with finite possibilities. You see, if space is infinite, then even though any specific arrangement of atoms is incomprehensibly unlikely, infinity guarantees it occurs infinite times. There are only so many ways to arrange matter within a given volume, a huge number but finite. In an infinite space, every possible arrangement must occur, and must occur infinitely often. There are infinite versions of you who made different choices at key life moments. Infinite versions where dinosaurs never went extinct. Infinite planets where evolution took radically different paths. Infinite regions where the laws of physics appear different because local conditions vary, even though underlying laws remain the same. This generates a profound philosophical problem. If infinite identical copies of you exist, which one is really you? Does personal identity even make sense in an infinite cosmos? When you make a decision, infinite versions of you make every possible alternative decision. Does your choice matter if all possibilities occur somewhere? These aren't merely abstract philosophical puzzles, they're genuine consequences of taking seriously the possibility that space extends infinitely. Cosmologist Max Tegmark has calculated that if the universe is infinite, the nearest identical copy of you exists approximately 10 to the power 1029 meters away, a number so large that writing it out would require more digits than atoms in the observable universe. That's comfortably beyond our observational horizon by an absurd margin, so you'll never meet your doppelganger. But the mere fact that infinity demands their existence forces us to reconsider what you means in the first place. Some physicists find these implications so disturbing that they prefer finite universe models. A positively curved universe that curves back on itself avoids infinite duplication while maintaining the advantages of having no boundaries. You'd exist only once, still in a universe billions of light years across, but definitely, uniquely, you. Personal identity retains clear meaning. The cosmos has grandeur without infinity's conceptual baggage. But here's what makes this question truly challenging. We might never have enough information to decide. If the universe is infinite, we can only observe our finite horizon within it. If the universe is finite but much larger than our observable region, we still only see our local patch. Both scenarios look identical from our perspective. We can measure curvature, but if the curvature is too gentle, We can't determine whether space is truly flat, infinite, or slightly curved, potentially finite. We're in the position of those hypothetical observers in Kansas trying to determine Earth's global shape from local measurements, possible in principle, but requiring precision beyond what we can currently achieve. The question, how big is the universe, might not have a meaningful answer if space is infinite. Infinity isn't a size, it's the absence of size limitations. You can't measure infinity. You can't meaningfully compare infinities using ordinary concepts of bigger or smaller. If the universe is infinite, then asking how big is like asking what color is Tuesday, a category error where the question itself doesn't match the reality it's trying to describe. Yet even if we can't answer whether the universe is infinite, we can explore what infinity would mean for structure, for possibility, and for our place in existence, and we can ask whether the universe is even the right category. What if our cosmos, everything within our Big Bang, whether observable or not, is itself just one finite region within something incomprehensibly larger? What if the universe is really a multiverse with our space being one bubble among infinite others? That possibility doesn't just make the cosmos bigger, it makes it bigger in a fundamentally different way, adding new dimensions to the concept of existence itself. Before we can explore that frontier, though, we need to understand what drives cosmic expansion. Because the answer to how big the universe is depends entirely on what happened at the beginning, what's happening now, and what will happen in the deep future. Space itself is doing something that seems impossible, and understanding this process is the key to understanding cosmic scale. Chapter 4. Expanding Fabric. Space isn't just empty volume where things happen. Space is something, a physical entity that can bend, ripple, expand, and potentially even tear. This is perhaps the most difficult concept in modern cosmology for people to grasp, because our everyday experience tells us that space is simply the absence of stuff, nothingness between objects. But general relativity reveals that space-time is a dynamic medium, as real as matter and energy, and it's been expanding since the Big Bang. When cosmologists say the universe is expanding, they don't mean galaxies are flying apart through space like shrapnel from an explosion. They mean space itself is stretching, carrying galaxies along with it. Imagine a loaf of raisin bread rising in an oven. From the perspective of any given raisin, all other raisins appear to be moving away. The raisins aren't moving through the dough. The dough is expanding and carrying them apart. Our universe is the dough, and galaxies are the raisins. This expansion isn't happening into anything. Space itself is what's expanding, and it doesn't need external space to expand into. The universe doesn't have an outside. Edwin Hubble's 1929 discovery of cosmic expansion came from observing galaxies and noticing something peculiar. Their light was shifted toward the red end of the spectrum, and this redshift increased with distance. Nearby galaxies showed little redshift. Distant galaxies showed substantial redshift. The relationship was linear. The farther the galaxy, the faster it appeared to be receding. This wasn't because galaxies were moving through space away from us. It was because space between us and those galaxies was expanding, stretching the wavelength of light during its journey to Earth. The expansion rate, now called the Hubble constant, describes how fast space is stretching. Current measurements place it around 70 kilometers per second per megaparsec, though, as mentioned earlier, different measurement methods yield slightly different values. What does this number mean practically? Take 2 points in space separated by 1 megaparsec, about 3.226 million light-years. Due to cosmic expansion, those points are moving apart at approximately 70 kilometers per second. 2 points separated by 2 megaparsecs are moving apart at 140 kilometers per second. The farther apart things are, the faster they're receding, not because they're accelerating through space, but because there's more space between them to expand. This leads to something that seems to violate physics. Galaxies can recede from us faster than the speed of light. Special relativity says nothing can move through space faster than light, but it says nothing about space itself expanding. If a galaxy is sufficiently distant, the expansion of all the space between us and it can accumulate to apparent recession velocities exceeding light speed. These galaxies aren't violating relativity, they're not moving through space faster than light. Space is growing between us faster than light can cross it. Right now, galaxies beyond approximately 14 billion light-years are receding faster than light. We can still see many of them because the light was emitted when they were closer and has been traveling toward us ever since. But we can never see their current state, only their ancient past. And galaxies beyond the cosmological event horizon, currently about 16 billion light-years away, are receding so fast that light emitted from them today will never reach us, no matter how long we wait. Space expands between us faster than light approaches. These galaxies have effectively vanished beyond an absolute observational boundary. What drives this expansion? For decades after Hubble's discovery, cosmologists assumed expansion was simply the aftermath of the Big Bang, gradually slowing due to gravity's attractive pull. Then came the 1998 supernova studies showing acceleration. Some unknown force, dubbed dark energy, is causing expansion to speed up rather than slow down. This energy comprises about 68% of the universe's total content, yet we have no idea what it actually is. It's not matter or radiation, it's something else, perhaps a property of space itself, a vacuum energy that creates repulsive gravity. The leading theoretical explanation is the cosmological constant, a term Einstein originally introduced into his equations, then later called his greatest blunder. Einstein added this constant to keep the universe static, as was believed in his time. When Hubble discovered expansion, Einstein abandoned the constant. But dark energy's discovery resurrected it with new meaning. If vacuum space has intrinsic energy, if empty space is untruly empty but seethes with quantum fluctuations, this could generate a small but persistent repulsive pressure. As space expands and creates more vacuum, this energy grows, driving ever faster expansion. Here's the disturbing implication. Dark energy dominance means our universe has entered an exponential expansion phase. The distance between gravitationally unbound structures grows exponentially over time. Eventually, in hundreds of billions of years, galaxies beyond our local group will accelerate past the cosmological event horizon and fade from view. The Milky Way, Andromeda, and a few dozen nearby galaxies will remain gravitationally bound in an island universe surrounded by an expanding void. Future astronomers in that distant era will observe a cosmos apparently consisting only of their local cluster, with no other galaxies visible anywhere. They'll have no evidence that the universe is expanding, no way to detect the cosmic microwave background, which will be redshifted into undetectability, and no obvious way to discover the Big Bang ever occurred. We're living in a special epoch where the universe's history is still observable, early enough that distant galaxies remain visible, and the cosmic microwave background provides clear evidence of cosmic origins, yet late enough that structure has formed and complexity has emerged. In a universe dominated by dark energy, our moment is transitory. A billion-year window of cosmic self-awareness before information about the universe's true nature fades beyond reach. But expansion also carries a silver lining for cosmic structure. Without it, the universe would have collapsed back on itself shortly after the Big Bang, crushed by its own gravity into a catastrophic Big Crunch. Expansion provides breathing room for structure to form, for gravity to pull matter together into galaxies, while space grows to prevent everything from collapsing into one supermassive black hole. Expansion allows the universe to have a history to evolve, to create conditions where complexity and life can emerge. The expansion rate also determines the universe's ultimate fate. If expansion eventually slows and reverses, everything could collapse in a big crunch. If expansion continues at constant rate, the universe experiences a big freeze. Stars burn out, galaxies fade, and everything grows cold and dark. If acceleration continues increasing, space might eventually tear itself apart in a big rip, ripping atoms and even subatomic particles asunder. Current observations favor the Big Freeze scenario with eternal expansion, but dark energy's nature remains mysterious enough that other fates can't be completely ruled out. Consider what expansion means for the concept of now. When you look at Andromeda, you see it as it was 2.5 million years ago, but what is Andromeda doing right now? The question seems simple, but relativity reveals it's actually meaningless. Simultaneity, the concept of two events happening at the same time, depends on reference frame. There's no universal now that extends across space. Different observers in relative motion have different definitions of simultaneity. In an expanding universe, this problem becomes even more profound. The present moment for a galaxy 10 billion light-years away is fundamentally ambiguous. You cannot point to a specific state of that galaxy and say, "This is happening now," in any objective sense. This doesn't just complicate communication, it makes the universe at this instant a concept without clear physical meaning. When we talk about the universe's size or age, we're referring to measurements made from our reference frame using our definition of time. An observer in a distant galaxy would calculate the same age for the universe because they'd measure the same time since the Big Bang, but their definition of now across space would slice through space-time differently than ours. The universe doesn't have a single present moment. It has countless overlapping presents, each valid from its own perspective. This relativistic complication adds yet another layer to the question of cosmic size. Not only is how big is the universe potentially unanswerable if space is infinite, and not only is much of the universe beyond our observational horizon, but even defining the universe at a specific instant requires choosing a reference frame. The cosmos resists simple description. Every attempt to pin it down with measurements reveals new subtleties that make straightforward answers elusive. Yet despite these complications, expansion remains one of the most empirically verified aspects of cosmology. Thousands of galaxy redshift measurements confirm it. The cosmic microwave background's temperature and pattern confirm it. The abundance of light elements forged in the Big Bang confirms it. Every independent line of evidence points to the same conclusion. Space has been expanding for 13.8 billion years, carrying matter and energy along with it, creating the observable cosmos we see today. Understanding expansion is fundamental to grasping cosmic scale, but expansion is only part of the story. To truly understand how big the universe became and what drove its growth, we need to explore a brief but crucial moment in cosmic history when space expanded faster than you can possibly imagine, a period called inflation. Chapter 5: Inflation's Moment. In the first fraction of a second after the Big Bang, something extraordinary happened. Space expanded exponentially, doubling in size over and over in rapid succession. This period, called cosmic inflation, was proposed by physicist Alan Guth in 1980 to solve several deep problems in cosmology. Without inflation, the universe's observed properties seem impossibly fine-tuned. The cosmic microwave background has nearly identical temperatures in all directions, varying by only 1 part in 100,000. Yet regions on opposite sides of the sky have never been in causal contact according to standard Big Bang theory. How did they coordinate to have the same temperature? Inflation solves this. Before inflation, the entire observable universe was a tiny region in thermal equilibrium. Inflation then stretched this small patch to enormous size, preserving its uniformity. Inflation also explains why space appears so geometrically flat. Imagine a balloon with a curved surface. If you expand the balloon enormously, any small region of its surface looks increasingly flat, like how Earth appears flat locally even though it's globally spherical. Inflation took whatever curvature the universe initially had and stretched it so dramatically that within our observable region, space appears flat to extraordinary precision. The universe could have global curvature, but we'd need to observe far beyond our horizon to detect it. What drove inflation? The leading theory involves a hypothetical scalar field called the inflaton field, which temporarily dominated the universe's energy density. While in a special high-energy state, this field generated enormous repulsive gravity, similar to dark energy but vastly more powerful, driving exponential expansion. When the inflaton field decayed to a lower energy state, inflation ended, and the field's energy converted into ordinary matter and radiation, effectively creating the hot, dense plasma of the traditional Big Bang picture. Inflation wasn't before the Big Bang. It was the Big Bang, or at least its earliest phase. Here's where cosmic scale becomes truly staggering. The observable universe, 93 billion light-years across, represents the region that inflated from a patch smaller than an atom. But inflation didn't just inflate our observable region, it inflated everything. If space extended beyond our pre-inflation patch, inflation would have expanded those regions too. Calculations suggest the full universe, the entirety of what inflated, is at least 1023 times larger than our observable region. That's a 1 followed by 23 zeros. If our observable universe were the size of a single atom, the full inflated universe would be millions of light-years across. And that might be a conservative estimate. Many inflation models produce a universe that's effectively infinite in size. If inflation lasted slightly longer than the minimum required to solve cosmology's problems, and many models predict it did, the universe expanded so enormously that finite size becomes meaningless. An infinite pre-inflation space would remain infinite after inflation, just vastly more spread out. A finite but large enough pre-inflation space would inflate to scales where calling it finite is technically accurate but practically irrelevant, like saying a volume containing 10^100 cubic light-years is finite, when that number exceeds anything meaningful. Inflation also had to end, and it didn't end everywhere simultaneously. Quantum fluctuations in the inflaton field meant different regions stopped inflating at slightly different times. Regions that inflated longer grew even larger. This creates a picture where our observable universe is one bubble in a vastly larger inflated space, with other bubbles scattered throughout. Each bubble would have slightly different properties based on exactly how inflation ended in that region. The physical constants, particle properties, even the effective laws of physics could vary between bubbles, though within each bubble conditions would be uniform. This is the beginning of multiverse theory, though we're not yet at its full implications. Even staying within our single inflated space, our universe in the traditional sense, the scale becomes incomprehensible. Every cubic meter of observable space was once crammed into a volume trillions upon trillions of times smaller. The expansion was so extreme that quantum fluctuations in the pre-inflation plasma were stretched to cosmic scales, becoming the seeds of galaxy clusters and the temperature variations we observe in the cosmic microwave background. The largest structures in today's universe started as quantum jitters in a patch of space smaller than a proton. Evidence for inflation comes from multiple sources. The cosmic microwave background's temperature variations match inflation's predictions with remarkable precision. The pattern of these fluctuations, slightly more variation at large scales than small, matches what inflation generates from stretched quantum noise. The flatness of space, the uniformity of temperature, and the distribution of matter all align with inflation's predictions. In 2014, scientists briefly thought they detected primordial gravitational waves from inflation in the cosmic microwave background's polarization. though later analysis showed the signal was actually from interstellar dust. The search for direct gravitational wave evidence continues. But inflation creates a conceptual problem almost as significant as the problems it solves. If quantum fluctuations could end inflation in some regions while it continued elsewhere, inflation never completely stops. In regions where it continues, space keeps inflating exponentially. Those regions themselves develop quantum fluctuations, some of which end inflation locally, while others continue it. This eternal inflation scenario suggests inflation, once started, creates an infinite tree of bubble universes, each with potentially different properties, branching forever into the future. Our universe would be one bubble in an eternally inflating multiverse. This raises profound questions about probability and prediction. If eternal inflation creates infinite bubble universes with varying properties, what becomes of physics' predictive power? We can't predict which bubble we should find ourselves in if all possibilities occur infinitely often. This measure problem in cosmology remains unresolved. Some physicists embrace eternal inflation and work on frameworks for making predictions despite the infinities involved. Others seek alternative models that generate an inflated universe without eternal reproduction. To put inflation's impact on cosmic scale in perspective, imagine compressing Earth's entire history into a single year. On this scale, the universe's 13.8 billion years of post-inflation evolution would correspond to roughly 1 year. Inflation itself, the period of exponential expansion, would last about 1/trillionth of a second in early January. Yet in that incomprehensibly brief instant, space expanded more than it has in all the billions of years since. Inflation did most of the work of making the universe big. Everything since then has been relatively slow, steady growth. What inflation reveals is that the universe's size aren't just large, it's large in a way that resulted from physical processes we can describe mathematically and test observationally. This isn't mysticism or speculation. This is physics backed by observation and successful prediction. The observable universe's properties make sense if inflation occurred. They're deeply puzzling if it didn't. While inflation remains a theory rather than confirmed fact, it's currently our best explanation for why the cosmos has the structure and scale we observe. Yet even accepting inflation and its implications for vast size beyond our horizon, we've still only discussed one universe, one inflated region resulting from one Big Bang. The deepest question about what lies beyond isn't about distance beyond our observable horizon. It's about whether entirely separate universes exist, disconnected from ours not by distance, but by fundamental separateness. Do other Big Bangs occur? Do other inflated regions exist beyond any possible causal connection to ours? Does the universe refer to one cosmos among many, or to everything that physically exists? These questions push us beyond observational cosmology into theoretical physics and philosophy, but they're not idle speculation. They emerge naturally from our best theories of fundamental physics, from quantum mechanics to string theory. The next frontier in understanding cosmic scale isn't measuring larger distances. It's confronting the possibility that distance itself becomes meaningless when considering what truly lies beyond. We're ready to explore the multiverse hypothesis, not as science fiction, but as a genuine possibility emerging from mainstream physics. Chapter 6: Parallel Worlds. The multiverse isn't a single theory. It's a collection of different scenarios emerging from different areas of physics that all suggest our universe might be one among many. Some multiverse concepts involve regions beyond our cosmic horizon. Others involve entirely separate space-times. Still others involve quantum branching at every moment. What they share is a radical implication. The totality of existence might be vastly larger and stranger than anything we can observe or even imagine observing. The Level 1 multiverse, as cosmologist Max Tegmark calls it, is simply the consequence of infinite space. If the universe extends infinitely beyond our observable horizon and contains matter at roughly uniform density, there must be other regions, other bubble observables out there. These regions wouldn't be separate universes in a fundamental sense. They'd be distant parts of the same space-time, the same continuum, just beyond our ability to observe. But they'd be causally disconnected from us. Light or information from those regions will never reach us, and our influence will never reach them. For all practical purposes, they might as well be separate universes. In an infinite space, all possible arrangements of matter within a given volume must occur somewhere, and must occur infinitely often. This leads to those infinite copies of you we discussed earlier, along with infinite variations. Every possible history that could play out in a region the size of our observable universe has played out somewhere. There are regions where World War II never happened, where Rome never fell, where dinosaurs evolved intelligence. Not because of different laws of physics, but simply because probability and infinity guarantee all possibilities occur. This level of multiverse is the simplest and least speculative. It requires only that space be infinite, which many cosmologists consider likely. The Level 2 multiverse emerges from eternal inflation. If inflation creates bubble universes continuously, each bubble could have different fundamental properties. The physical constants, the strength of gravity, the mass of electrons, the speed of light, might vary between bubbles. Not arbitrarily, but based on how symmetries broke when inflation ended in each region. In our bubble, the electromagnetic force has one strength. In another bubble, it might be slightly stronger or weaker, dramatically affecting chemistry and preventing atoms as we know them from forming. Most bubbles would be sterile, incapable of supporting complexity or life. We exist in a bubble with properties permitting life, not because our bubble is special, but because observers can only exist in bubbles with observer-permitting properties. This addresses the fine-tuning problem in physics. Our universe's constants appear remarkably well-tuned for life. If gravity were slightly stronger, stars would burn out quickly, leaving no time for life to evolve. If the strong nuclear force was slightly weaker, atomic nuclei wouldn't hold together and chemistry couldn't exist. If the cosmological constant were much larger, space would expand so fast that galaxies could never form. These coincidences seem to require explanation. The multiverse provides one. In an ensemble of universes with varying constants, life emerges in the rare bubbles where conditions permit it. We observe fine-tuning because we couldn't exist in unfine-tuned universes to observe their properties. Critics argue this anthropic reasoning is unfalsifiable and therefore unscientific. If every possible configuration exists somewhere in a multiverse, any observation becomes compatible with the theory. You can't falsify a multiverse by observing our universe's properties, because the multiverse predicts some bubbles will have exactly our properties. But proponents counter that the multiverses aren't an arbitrary hypothesis invented to explain fine-tuning. It's a natural consequence of inflation, which was developed to solve completely different problems and happens to generate multiple bubble universes as a side effect. The Level 3 multiverse comes from quantum mechanics. The famous double-slit experiment shows that particles behave as waves of probability until measured, at which point they collapse into definite states. But what causes collapse? The many worlds interpretation proposed by Hugh Everett in 1957 suggests collapse doesn't happen. Instead, every quantum possibility occurs in separate branches of reality. When you measure a particle and find it in one location, the universe splits. In one branch, the particle is here. In another branch, the particle is there. Both outcomes occur, you just experience one branch. If many worlds is correct, the universe branches continuously at inconceivable rates. Every quantum event, and there are countless trillions every second, spawns new branches. Each branch is equally real, a separate universe where different outcomes occurred. There are branches where you made different choices at every decision point, branches where different mutations occurred during evolution, branches where quantum fluctuations in the early universe produced entirely different cosmic structures. These parallel worlds don't exist somewhere else in space. They exist in parallel configurations of quantum reality, separate but equally actual. Many worlds generates philosophical vertigo if every possibility occurs in some branch. Do your choices matter? If there's a branch where you made the opposite choice, does personal responsibility have meaning? Physicists debate whether many worlds is true science or unfalsifiable metaphysics. It makes no new predictions distinguishing it from other quantum interpretations because we can only observe our branch. Yet, it solves quantum mechanics conceptual problems with mathematical elegance, requiring no special collapse mechanism, just straightforward evolution of the quantum wave function. The Level 4 multiverse is the most speculative and mathematical. It proposes that every mathematically consistent structure exists physically somewhere. Our universe has specific mathematical structure, particular symmetries, particular equations governing physics. But other mathematical structures, equally consistent, could describe universes with entirely different laws. A universe where time has multiple dimensions, where space isn't continuous, where gravity is attractive in 3 dimensions but repulsive in others. If mathematical existence implies physical existence, then reality isn't one universe or even a multiverse of varying constants. It's the complete ensemble of all possible mathematical structures. This ultimate ensemble, as physicist Max Tegmark calls it, would contain not just universes with different constants, but universes with entirely different rules. Most would be far too simple or too chaotic to support observers. Some might be impossible to visualize, their structure so alien that our brains couldn't conceptualize them. We'd exist in a structure complex enough to generate observers, but simple enough that physics remains comprehensible. The question why these laws of physics would be answered. All possible laws exist somewhere. We observe ours because it's among the rare sets permitting observation. String theory, the leading candidate for unifying quantum mechanics and general relativity, may require something like a multiverse. String theory predicts extraspatial dimensions beyond the 3 we experience, curled up at tiny scales. The specific way these dimensions curl determines the universe's properties, particle masses, force strengths, physical laws. But string theory offers roughly 10⁵00 possible ways for these dimensions to configure themselves, each yielding a different universe with different physics. This landscape of possibilities suggests eternal inflation might produce bubble universes exploring different regions of the landscape, creating a vast ensemble of universes with string theory-allowed physics. Confronting the multiverse idea forces a shift in how we think about scientific explanation. Traditionally, science seeks unique explanations, one set of laws, one history, one universe. The multiverse suggests reality is far more extravagant. Explanation becomes statistical. We observe what we observe because it's among the possibilities compatible with observers existing. This anthropic reasoning bothers many physicists who prefer explanations deriving our universe's properties from fundamental principles rather than selection effects. Yet if the multiverse is real, anthropic reasoning becomes necessary, not a failure of explanation but an acknowledgement of how observation works in an ensemble reality. The multiverse remains controversial. Some physicists embrace it as a natural consequence of our best theories. Others reject it as unfalsifiable speculation beyond science's domain. Still others work to find ways to test multiverse predictions, perhaps through subtle patterns in the cosmic microwave background, or through careful analysis of fundamental constants. The debate continues not because scientists can't agree, but because we're genuinely uncertain. The multiverse might be reality's deepest truth or a theoretical mirage. We don't yet know. What we do know is this: every attempt to understand the universe's size leads to bigger questions. Measuring the observable universe reveals vast scales. Considering inflation suggests immensely larger regions beyond observation, contemplating eternal inflation produces infinite bubble universes. Accepting quantum mechanics might require infinite parallel branches. Pursuing mathematical consistency potentially implies infinite mathematical universes. Each step outward multiplies existence by orders of magnitude until size becomes inadequate language for describing reality is scope. But all these multiverse scenarios share an assumption that our understanding of physics, mathematics, and logic applies everywhere. What if reality extends beyond even our conceptual frameworks? What if existence includes aspects we can't mathematically describe or logically comprehend? These questions push us to the absolute boundary of meaningful inquiry, where science approaches philosophy and both encounter fundamental limits. We're ready to confront what might lie beyond even the multiverse, the ultimate edge of knowability itself. Chapter 7. Knowledge Boundaries. There are things we don't yet know but could potentially discover. Then there are things we can never know, not because of technological limitations, but because of fundamental limits built into reality itself. The boundary between unknown and unknowable isn't always clear, but physics reveals several absolute barriers beyond which information simply cannot reach us, no matter how advanced our technology becomes. These boundaries define not just what we can measure about the universe, but what can meaningfully exist in our observable reality. The most obvious boundary is the cosmic event horizon, the limit beyond which cosmic expansion prevents light from ever reaching us. Galaxies beyond this horizon, currently about 16 billion light-years away, are receding so rapidly that photons emitted toward us are swept backward by expanding space faster than they can approach. We might currently see these galaxies' ancient light from when they were closer, but we'll never see their present state or future evolution. They've crossed an absolute observational boundary, separated from us not by distance that could eventually be crossed, but by the structure of space-time itself. As dark energy continues accelerating expansion, this horizon will actually move inward. Galaxies currently within reach will cross the threshold and fade to invisibility. Over hundreds of billions of years, our observable universe will shrink. The local group, Milky Way, Andromeda, and nearby dwarf galaxies will merge into one large galaxy surrounded by darkness. Future observers will have no evidence that other galaxies ever existed, no way to measure cosmic expansion, no access to the cosmic microwave background. They'll be cosmologically isolated, unable to discover the universe's true nature through observation. This reveals something profound. Cosmological knowledge is time-sensitive. We exist during a brief window, roughly 10 billion years wide, when the universe's history remains observable. Earlier, stars and galaxies hadn't formed. Later, cosmic expansion will erase evidence of cosmic origins. Our moment is special not because physics is different now, but because information about cosmic history is currently accessible. In the deep future, that information will be gone, not destroyed, but rendered permanently inaccessible beyond an ever-shrinking horizon. Knowledge itself has boundaries in time as well as space. Black holes create another absolute information boundary. The event horizon of a black hole marks the surface beyond which nothing, not even light, can escape. Any information that falls past the event horizon becomes permanently inaccessible to outside observers. You could watch something approach the horizon, seeing it slow and redshift due to extreme time dilation, but you'd never see it cross. From the falling object's perspective, it crosses smoothly and continues to the singularity, but from outside it asymptotically approaches the horizon forever, never quite crossing in finite external time. What happens to information inside a black hole generated the black hole information paradox that puzzled physicists for decades. Quantum mechanics says information cannot be destroyed. The universe's quantum state always evolves deterministically. But general relativity says anything crossing an event horizon is lost forever. These principles seemed incompatible. Stephen Hawking's discovery that black holes emit radiation due to quantum effects near the horizon partially resolved this. Hawking radiation causes black holes to slowly evaporate over astronomical timescales, potentially releasing information in scrambled form. But exactly how information escapes remains debated, touching the deepest questions about quantum gravity. Black holes demonstrate that the universe contains regions fundamentally separated from our ability to observe. Every black hole event horizon is a boundary beyond which physics remains theoretical. We can calculate what equations predict, but can never empirically verify those predictions from outside. This doesn't make black hole physics unscientific, but it does reveal limits to direct observation. Much of physics involves inference from accessible evidence about inaccessible domains. Quantum mechanics imposes its own knowledge limits through the Heisenberg uncertainty principle. You cannot simultaneously know a particle's exact position and exact momentum. Measuring one with perfect precision renders the other completely uncertain. This isn't a measurement technology limitation, it's fundamental to reality. Particles don't have definite position and momentum simultaneously. The universe itself doesn't contain this information. Asking for both values simultaneously is asking for something that doesn't exist, like asking for the smell of the color blue. This quantum fuzziness affects cosmology. Inflation stretched quantum fluctuations to cosmic scales, creating the seeds of galaxies. But quantum mechanics fundamentally limits how precisely we can know the initial conditions. Even with perfect observations of today's universe, we couldn't exactly reconstruct the quantum state of the early universe because quantum uncertainty erases that information. The past, beyond a certain precision, is fundamentally unknowable, not because evidence was destroyed, but because reality never contained that level of specificity. Gödel's incompleteness theorems from mathematics reveal another kind of limit. Any sufficiently complex logical system contains true statements that cannot be proven within that system. Applied to physics, this suggests our theories might never achieve complete self-contained explanation. There might be true facts about the universe that cannot be derived from any finite set of axioms or equations. Our best theory might successfully describe everything observable, yet still leave fundamental questions unanswerable, because those answers transcend the logical framework our minds can construct. This doesn't mean science ends or becomes futile. It means ultimate complete knowledge might be impossible in principle, not just practice. We can continue learning indefinitely, developing deeper theories and more precise observations, yet never reach final answers to every question. The universe might be fundamentally more complex than any complete description we could formulate, always containing aspects beyond our current theoretical framework. Consider the question, why do the laws of physics have the form they do? We can discover those laws, test them, use them for prediction and technology, but explaining why reality follows these particular rules rather than others might require standing outside physical reality to examine it, impossible by definition. If you're embedded in a system, you might not be able to deduce why that system has its particular structure. Some questions might be unanswerable not because we're not smart enough, but because any intelligence embedded in reality faces the same fundamental limits. The simulation hypothesis illustrates this limit. If we're living in a sophisticated computer simulation created by advanced beings, could we ever prove it? Maybe, if the simulators left detectable glitches or signatures. But if the simulation is perfect, mimicking a real universe flawlessly, no observation from within could distinguish simulation from base reality. The question might be empirically meaningless, not false, but undecidable from our perspective. Reality's ultimate nature might transcend our ability to investigate. These boundaries, cosmic horizons, black hole event horizons, quantum uncertainty, mathematical incompleteness, embedded perspective limitations, aren't failures of science. They're features of reality itself, mapped by science's successes. Recognizing limits is itself progress. Knowing what we can't know focuses effort on questions that have answers and prevents wasted time pursuing impossibilities. Science's power comes partly from accepting its boundaries rather than claiming omniscience. Yet accepting limits doesn't mean abandoning wonder. The unknowable isn't empty or boring, it's the ultimate mystery. Beyond every horizon, cosmic or conceptual, lies an infinity of things we'll never observe, never measure, never fully understand. This doesn't diminish our knowledge, it contextualizes it. Every fact we've learned, every structure we've mapped, every law we've discovered, all of it exists against a backdrop of vastness that extends beyond measurement, beyond observation, beyond conception. You might feel this is unsatisfying. We want complete answers, total understanding, the comfort of knowing reality entire. But perhaps this incompleteness is itself meaningful. If existence was small enough to be fully comprehended, it would be smaller than the minds trying to comprehend it, an absurdity. The universe's size in all its dimensions guarantees there's always more to discover, always deeper mysteries, always further horizons. Knowledge boundaries aren't walls-ending inquiry. They're invitations to appreciate that reality is bigger in size, complexity, and mystery than any description will ever complete. This brings us to a question that encompasses all we've discussed. What does it mean to exist in a universe this large, this old, this mysterious? We've measured distances, contemplated infinities, explored multiverses, and confronted unknowability. But we haven't yet asked the most human question. What does cosmic scale mean for us? How should understanding these vastnesses affect how we think about life, meaning, and our place in existence? These aren't scientific questions exactly, but they're questions science enables us to ask with new depth. Chapter 8. Perspective. Stand outside on a clear night and look up. Every star you see is within a few thousand light years, cosmic neighbors in galactic terms, all residents of a tiny patch of the Milky Way. The farthest object visible to your naked eye is Andromeda, 2.5 million light years away, appearing as a faint smudge. Everything else, the billions of galaxies scattered across billions of light years, requires telescopes to detect. Your unaided eye can access less than 1/trillionth of the observable universe's volume. You're seeing an incomprehensibly small sample of reality, yet even that fraction contains more stars than you could count in a lifetime. This is the first perspective shift cosmic scale demands, recognition of just how local our direct experience is. Every sunrise you've seen, every landscape you've encountered, every person you've met, all of it confined to one planet, one star system, one infinitesimal point in space. All of human history, every civilization that's ever existed, every war fought and peace made, every work of art created and scientific discovery achieved, all of it has occurred on this tiny world orbiting an ordinary star in an unremarkable region of a typical galaxy. In cosmic terms, we've barely left home. We're infants taking our first tentative steps, learning to comprehend a reality far vaster than our ancestors ever imagined. Carl Sagan captured this beautifully after Voyager. One photographed Earth from beyond Neptune in 1990. He called our planet a pale blue dot, a pixel in a sunbeam, nearly invisible against the cosmic dark. Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on that dot. Every triumph and tragedy, every moment of joy and suffering contained within that pale blue pixel suspended in darkness. The photograph forces perspective. All our concerns and conflicts happen on a stage so small it nearly vanishes against the backdrop of space. Yet here's the paradox. Cosmic insignificance coexists with cosmic significance. Yes, Earth is tiny and humans are transient, but we're also the part of the universe that has become conscious of itself. We're matter that organized itself into configurations capable of understanding matter. We're atoms that can contemplate their own origin in stellar furnaces. The carbon in your bones, the oxygen you breathe, the iron in your blood, all of it was forged in the cores of dying stars that exploded billions of years ago, scattering their enriched material into space. You are literally made of stardust, not metaphorically, but factually. Your existence connects directly to the largest cosmic processes. This connection runs deeper than chemical composition. Your consciousness, your ability to think, feel, and understand, emerges from complexity that took billions of years to develop. The early universe was simple: hydrogen, helium, radiation, and darkness. No stars, no planets, no life. Over time, gravity pulled matter together. Stars ignited, fusing light elements into heavier ones. Generations of stars lived and died, each one increasing the universe's chemical complexity. Planets formed from this enriched material. On at least one planet, probably many more, chemistry became biology. Simple organisms evolved into complex ones. Eventually, nervous systems developed sophisticated enough to generate subjective experience and abstract thought. You're not an accident in an indifferent universe. You're the outcome of processes that have been operating since the beginning. The universe has been building toward complexity, creating stars, planets, chemistry, biology, and minds. Whether this tendency toward complexity is purposeful or simply how physics unfolds remains debatable, but the fact is undeniable. The universe created conditions for you to exist and to understand. In some sense, through you, the universe observes itself. Your thoughts about cosmic scale are the universe's thoughts about itself. This isn't mysticism, it's simply acknowledging that you're not separate from the cosmos. You're an integral part of it. Cosmic scale also forces reconsideration of what matters. From one perspective, nothing matters. We're microscopic beings on a tiny world in an unimaginably vast cosmos that will continue long after we're gone. Empires rise and fall, individuals live and die, and the universe continues indifferent to all of it. This nihilistic view follows logically from cosmic scale. If we're this insignificant, why does anything matter? But there's an equally valid opposite conclusion. If the universe is this vast and ancient, and you happen to exist within it for a brief moment, your existence is statistically extraordinary. You're a rare emergence of consciousness in a cosmos where most space and time contains no observers. You're privileged to experience this particular moment in cosmic history when stars still shine, galaxies are visible, and complexity flourishes. Instead of cosmic scale making life meaningless, it makes life precious precisely because it's rare, brief, and improbable. Moreover, cosmic scale doesn't diminish human concerns. It contextualizes them. Yes, your problems are small compared to colliding galaxies or the heat death of the universe, but they're real to you, occurring at the scale where consciousness operates. Pain hurts no less because it's happening on a small planet. Love matters no less because it's felt by beings who will die. Meaning doesn't require cosmic significance. It emerges from relationships, experiences, and choices at human scales. Recognizing cosmic vastness doesn't invalidate human experience. It adds layers of context to it. Some people find cosmic scale terrifying. The vastness induces existential vertigo, a sense of being lost in uncaring infinity. Others find it liberating. If the universe is this large, your mistakes and embarrassments are truly insignificant, freeing you from excessive self-consciousness. Both responses are valid. Cosmic perspective doesn't dictate how you should feel. It provides a framework within which feelings occur. You're free to find cosmic scale frightening, inspiring, humbling, exhilarating, or all of these simultaneously. What cosmic scale undeniably does is challenge anthropocentrism, the assumption that humans are central to reality's purpose. We're not. Earth isn't the center of the universe. The sun isn't special. Our galaxy is one among trillions. If intelligent life exists elsewhere, which seems statistically likely given the vastness, we're not even unique as observers. Humanity is one instance of consciousness in a cosmos that might contain countless others, each with their own perspective, none privileged over others. This has profound implications for how we treat our planet and each other. We're all inhabitants of the same cosmic lifeboat, temporary custodians of a rare world in a vast and mostly lifeless cosmos. The borders we draw, the conflicts we wage, the divisions we create, all of it happens on one small planet that, from cosmic perspective, is a unified whole. The photograph of Earth from space shows no borders, no divisions, just one fragile biosphere surrounded by darkness. Perhaps cosmic perspective can inspire better planetary stewardship and greater human cooperation. If we truly grasped how isolated and rare we are, we might treat our world and each other with more care. Yet cosmic scale also suggests that human choices genuinely matter in an unexpected way. If the multiverse is real and infinite, every possible choice occurs in some branch or bubble. But that doesn't make your choices meaningless. It means you determine which branch you experience. You can't control what happens in other universes, but you absolutely determine what happens in yours. Your decisions create your experienced reality, even if other versions of you make different choices elsewhere. Personal responsibility remains intact even in infinite existence. The ultimate perspective shift cosmic scale offers is this: you're simultaneously insignificant and essential. Insignificant in scope, one mind among potentially countless others in a vast cosmos. Essential in experience, you're the center of your observable universe, the only consciousness you directly access. Both truths coexist without contradiction. You're not the center of reality, but you are the center of your reality. The universe is incomprehensibly large, yet your existence within it is utterly unique and unrepeatable. This paradox, tiny yet significant, transient yet connected, is perhaps the deepest truth cosmic scale teaches. You don't have to choose between cosmic humility and personal meaning. You can embrace both. You can recognize that Earth is a dust mote in infinite space while simultaneously knowing that this dust mote contains everything you'll ever experience and everyone you'll ever love. You can accept that the universe will continue long after humanity vanishes, while still caring deeply about the present moment and the people in it. Understanding cosmic scale changes something fundamental about consciousness itself. Before you knew these truths, you might have imagined the universe was smaller, more comprehensible, perhaps designed with humans in mind. Now you know it's vastly larger than human concerns, operating on time scales that make civilizations seem like flickers, containing structures that dwarf everything we've built. This knowledge can't be unknown. Once you truly grasp cosmic scale, you carry it with you, coloring every experience with awareness of the larger context. Some of history's greatest scientists reported experiencing profound wonder when confronting cosmic immensity. Einstein described a cosmic religious feeling when contemplating the universe's order and scale. Sagan spoke eloquently about the privilege of being star-stuffed, contemplating the stars. These weren't mystical experiences disconnected from science. They were responses to scientific understanding, emotional reactions to empirical truths about reality's scope. Wonder isn't separate from knowledge. It's knowledge's natural companion when that knowledge concerns something as magnificent as the cosmos. You might ask, if the universe is this big, does God exist? Cosmic scale doesn't answer that question, but it reframes it. If a creator exists, they created something almost incomprehensibly extravagant. Trillions of galaxies, most of them beyond human observation, many containing no observers at all. Why create so much empty space? Theological answers vary. Perhaps the creator values grandeur for its own sake. Perhaps consciousness requires a vast stage to emerge. Perhaps we can't comprehend divine motivations. Or perhaps no creator exists and the universe is simply how physical law unfolds. Cosmic scale doesn't resolve these questions, but it makes clear that any creator must operate at scales far beyond human-focused narratives. What cosmic scale definitely demonstrates is that reality is stranger and more magnificent than our ancestors imagined. Every generation thought they understood the universe's size, and every generation was proven wrong by the next. Ancient peoples thought Earth was everything. Medieval scholars thought the solar system was everything. Early 20th century astronomers thought the Milky Way was everything. Each expansion of knowledge revealed a larger cosmos. We might feel we've finally reached the true scale, but history suggests we're probably wrong again. Future discoveries might reveal that even our current conception, observable universe, inflation, possible multiverse, is still just a fraction of reality's full scope. This epistemic humility is another lesson from cosmic scale. The universe has repeatedly proven itself larger than we expected. We should expect future surprises. What seems like the edge of knowledge today will likely prove to be another horizon with something beyond it. This doesn't mean science is futile or uncertain. Every measurement we've made is still valid. Every law we've discovered still applies within its domain. But it means our picture of reality, however accurate, is probably incomplete in ways we can't yet imagine. Living with cosmic perspective means balancing multiple scales simultaneously. You can appreciate a sunset while knowing Earth is one planet among billions. You can love someone deeply while recognizing that relationship exists in an incomprehensibly vast cosmos. You can work toward human goals while acknowledging that from cosmic perspective, those goals are microscopically local. These scales don't cancel each other out, they coexist, each valid at its own level. The universe operates at every scale simultaneously, from quantum fluctuations to cosmic structures, and you exist at multiple scales too. As a collection of atoms, a biological organism, a conscious being, a member of a species, an inhabitant of a planet, a constituent of a galaxy, a point in space-time, a configuration of universal matter. What then should you do with this knowledge? There's no single answer. Some people draw inspiration for scientific careers, wanting to contribute to humanity's understanding of these vast scales. Others find motivation for environmental protection, recognizing Earth's rarity. Still others experience existential freedom, liberated from taking everyday concerns too seriously. Some deepen spiritual practice, seeking connection with the larger whole they're part of. Others focus more intensely on human-scale relationships, recognizing their preciousness against cosmic vastness. All these responses are legitimate ways of integrating cosmic perspective. Perhaps the most profound implication is simply this: you're part of something far larger and longer lasting than yourself, yet your experience of that something is utterly unique. No one else has your exact perspective on existence. No one else sees the universe from precisely your location in space and time, filtered through your particular consciousness. When you look at the stars, you're engaging in an act of observation that connects you to billions of years of cosmic history and potentially to other observers scattered across space. You're lonely, possibly one consciousness among vast emptiness, and connected, made of material linking you to the entire cosmos. The universe is big in ways that transcend mere measurement. It's big enough to contain everything you'll ever know and infinite mysteries beyond that. It's old enough to have created elements, stars, planets, and life through patient physical processes. It's structured enough to be comprehensible, yet complex enough to always exceed complete understanding. And somehow, impossibly, you exist within it, conscious and aware, able to contemplate these truths. That fact, your existence as an aware being in this vast cosmos, might be the most remarkable truth of all, but we're not done yet. We've explored the universe's size and contemplated our place within it. One question remains: what happens next? How will this vast cosmos evolve? What's the universe's ultimate fate, and what might that mean for existence itself? To answer these questions, we need to project forward across billions and trillions of years, following cosmic evolution to its possible endpoints. The universe's future is as extraordinary as its past, and understanding it completes the picture of just how big, in time as well as space, reality truly is. Chapter 9. Ultimate Fate. The universe has a future, and that future is strange beyond imagining. If you could watch cosmic evolution in fast forward, speeding through billions and trillions of years, you'd witness transformations as profound as anything in the past. Stars will die, galaxies will darken, black holes will evaporate, and eventually, if current understanding holds, the universe will reach a state so different from today that empty seems an inadequate description. Understanding the universe's fate requires accepting that our current cosmic era, the age of stars and galaxies, is a brief phase in a much longer story. The immediate future, on cosmic timescales, is relatively straightforward. For the next several trillion years, star formation will continue as galaxies convert gas into new suns. But the universe's gas supply is finite. Most hydrogen will eventually be locked in stars, stellar remnants, or scattered too diffusely to collapse. Star formation will peak and then decline. Within about 1 trillion years, roughly 70 times the current age of the universe, the last new stars will ignite. After that, the cosmos will be lit only by stars that already exist, slowly burning through their remaining fuel. Different types of stars have vastly different lifespans. Massive stars burn hot and fast, exhausting their fuel in mere millions of years. Sun-like stars last about 10 billion years. Red dwarfs, the smallest, coolest stars, can burn for 10 trillion years or more, sipping their hydrogen supply so slowly that none have yet exhausted it in our 13.8 billion-year-old universe. These red dwarfs will be the last stars shining. Around 100 trillion years from now, even the longest-lived red dwarfs will finally sputter out, their fuel exhausted. At that point, no nuclear fusion will occur anywhere in the universe. The age of starlight will end. What remains after stars die depends on their mass. Sun-like stars become white dwarfs, Earth-sized remnants supported by electron degeneracy pressure, slowly cooling over trillions of years. Massive stars either explode as supernovas, leaving behind neutron stars, or collapse directly into black holes. These stellar remnants, white dwarfs, neutron stars, and black holes will dominate the post-stellar universe, along with cold planets, asteroids, and frozen gas clouds. The cosmos will be dark except for the faint infrared glow of cooling white dwarfs and the occasional burst of light when objects collide. But even this dark age isn't stable. On extremely long time scales, beyond 10 to 30 years, quantum tunneling and gravitational interactions will disrupt structures. Planets will be ejected from solar systems or spiral into stellar remnants. Galaxies, having merged through gravitational attraction into massive elliptical galaxies, will gradually lose stars as gravitational encounters fling them into intergalactic space. The organized structures we see today, solar systems, galaxies, galaxy clusters, will slowly dissolve through random gravitational interactions operating across inconceivable time spans. Around 10 to 40 years from now, another exotic process begins: proton decay. If protons are unstable, and some theories of particle physics predict they will eventually decay into lighter particles. Current experiments have shown that if proton decay occurs, the average lifetime exceeds 10^34 years. But given enough time, even improbable decays happen. If protons decay, all atomic nuclei will eventually disintegrate. White dwarfs, neutron stars, planets, anything made of atoms, will slowly dissolve into radiation and lighter particles. The the familiar matter of our universe will cease to exist in recognizable form. Even if protons are stable, black holes ensure nothing lasts forever. Stephen Hawking discovered in 1974 that black holes aren't truly black. They emit radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to lose mass, very slowly evaporating over time. The evaporation rate is inversely proportional to mass. Stellar mass black holes take about 10·67 years to evaporate, while supermassive black holes at galactic centers require 10·100 years or more. But given enough time, even the largest black holes will evaporate completely in a final burst of radiation. By 10⁻100 years, sometimes called the Google year, black hole evaporation will be nearly complete. The universe will contain mostly photons, neutrinos, electrons, and positrons, all spread across vast distances by continued expansion. The temperature will approach absolute zero. Structures won't exist, just isolated particles separated by distances that make current cosmic voids seem crowded. This is the heat death of the universe, a state of maximum entropy where no organized structures can form and no energy can flow from hot to cold because everything is uniformly cold. But wait, there's more. If dark energy continues accelerating expansion indefinitely, the universe will keep growing exponentially. The space between particles will increase without bound. Eventually, even atoms, if they still exist, would be torn apart by expansion in a scenario called the Big Rip. This would occur if dark energy becomes stronger over time, perhaps around 200 billion years from now, though current observations suggest dark energy has constant strength, making Big Rip unlikely but not impossible. The most probable scenario based on current evidence is a big freeze, eternal expansion at accelerating rates driven by constant dark energy, leading to a cold, dark, diffuse universe growing forever colder and more spread out. In this future, our observable universe's eventual state will be a diffuse gas of elementary particles, each separated from others by distances exceeding the size of today's entire observable universe. Information will still exist in principle, the quantum state of these particles, but nothing complex enough to process that information will remain. No stars, no planets, no life, no observers, just particles drifting through ever-expanding darkness. This might seem depressing, the ultimate futility of existence writ large. If the universe's fate is cold, dark, and lifeless, what's the point of anything? But consider several responses to this. First, the timescales involved are so vast they're almost meaningless. We're discussing 10 to 100 years, a one followed by 100 zeros. For comparison, the universe is currently 10^10 years old, 10 billion years. We're talking about futures trillions of times longer than the universe's current age. The stellar era, the time when stars shine, constitutes a tiny fraction of cosmic history, but it's the fraction we inhabit. Second, these distant futures aren't certain. They're extrapolations based on current physics, assuming no undiscovered phenomena intervene. History suggests surprises occur. We didn't predict dark energy until we observed it. We don't understand dark matter's nature. We don't know if protons decay or if quantum gravity effects become important at large scales. Physics might contain surprises that alter the universe's fate in ways we can't currently imagine. The heat death scenario is our best current estimate, not certain knowledge. Third, even if the universe's ultimate fate is heat death, that doesn't retroactively render current existence meaningless. Meaning isn't conferred by eternity. A beautiful sunset doesn't become less beautiful because it ends. A piece of music isn't meaningless because it finishes. Life doesn't require permanence to have value. The fact that consciousness and complexity exist now, even if they're temporary in cosmic terms, is extraordinary. You get to experience this brief window of cosmic time when stars shine and complexity flourishes. That's a privilege, not a futility. Some physicists and philosophers speculate about even more exotic far futures. Perhaps advanced civilizations could harvest energy from black hole rotation or manipulate dark energy to create local regions of slower expansion, extending the era of complexity. Perhaps consciousness could transfer to substrates less dependent on stars and planets, configurations of electromagnetic fields, or patterns in quantum foam. These speculations venture beyond established physics into imaginative territory, but they remind us that intelligence might find ways to persist or adapt to changing conditions. Roger Penrose has proposed an even more radical idea: conformal cyclic cosmology, suggesting the universe undergoes infinite cycles. The heat-death end state, containing only massless particles, becomes mathematically equivalent to a Big Bang-like beginning. The universe could restart, in a sense, with what we call the end of one cosmic era serving as the beginning of the next. This remains speculative, but it illustrates that even the universe's ultimate fate remains uncertain. There's also the possibility that the universe ends differently than heat-death predicts. If dark energy's strength changes, or if unknown instabilities exist in the fundamental fields underlying reality, the universe could undergo a vacuum decay event. A tiny region of space could tunnel to a lower energy state, creating a bubble of new physics that expands at light speed, transforming everything it touches. If this occurs, we'd never see it coming. The bubble edge would arrive at light speed, giving zero warning. One moment the universe exists as we know it. The next physical laws have changed. This seems unlikely but remains possible. What all these scenarios share is incomprehensible timescales, whether heat death, big rip, vacuum decay, or something unexpected. The universe's fate will unfold over periods so long that the entire age of stars and galaxies, including all of human history and any civilizations yet to come, represents a brief opening chapter in a vastly longer story. We're living in the universe's youth, when it's still energetic and dynamic. Everything that seems permanent, stars, galaxies, the laws of physics, is temporary when viewed against the full scope of cosmic time. Your existence occurs at a special moment, late enough for complexity to have evolved, early enough that the universe is still bright and filled with structure. Observers in the distant past would see a simpler universe. Observers in the distant future, if any exist, would see a darker one. You're in the sweet spot, the brief epoch when the cosmos is old enough to generate observers and young enough to provide them something interesting to observe. This temporal positioning isn't privileged in any cosmic sense, but it's extraordinarily fortunate. You get to see the universe in its prime. Understanding the universe's fate completes the picture of cosmic scale. The universe isn't just big in space, it's big in time, stretching from the Big Bang 13.8 billion years ago to futures trillions of years hence. Your entire civilization's existence, from the first human to the last, will occupy a temporal window smaller compared to cosmic time than a single human heartbeat compared to human lifespan. Yet within that heartbeat, you're conscious, aware, thinking about these immensities. That remains extraordinary regardless of what comes after. We've journeyed from measuring the observable universe to contemplating multiverses, from understanding inflation to accepting unknowability, from recognizing our cosmic insignificance to finding meaning despite it, from exploring the present to projecting into impossible futures. One question ties all this together. Having learned how big the universe is in space, in time, in complexity, in mystery, what does this mean for the deepest question of all? Not just how big is the universe, but why does it exist at all? And why are we here to ask? Chapter 10, Existential Meaning. We've reached the boundary where cosmology meets philosophy, where measurements give way to meaning, where how questions become why questions. Science has revealed a universe almost incomprehensibly vast in space, ancient in time, complex in structure, and mysterious in scope. But science, by its nature, doesn't answer why the universe exists in the first place. or why it has the particular properties that allow observers like us to emerge. These questions might have no scientific answers, or the answers might lie beyond our current frameworks entirely. The deepest mystery isn't the universe's size or age, its existence itself. Why is there something rather than nothing? Nothing would seem simpler. No space, no time, no matter, no energy, no laws of physics, just nothing. Yet here we are, embedded in a vast cosmos filled with galaxies, stars, planets, and life. Existence itself, the fundamental fact that anything is real, is so obvious we rarely notice how profoundly strange it is. Every explanation for why the universe exists seems to require something else that already exists. If God created the universe, why does God exist? If the universe emerged from quantum fluctuations, why do quantum fields exist? If mathematical structures exist necessarily, why does mathematics exist? Every answer pushes the question back one level without resolving it. Some philosophers argue this question is meaningless or unanswerable. Perhaps existence has no explanation because it's simply the ground state of reality. Asking why existence exists is like asking why logic is logical. These things might be fundamental in a way that precludes deeper explanation. Alternatively, perhaps our minds evolved to understand survival-relevant phenomena and are simply incapable of grasping why existence itself occurs. Just as a dog can't understand calculus, perhaps humans can't understand the deepest truths about reality's origin. But let's explore what answers various frameworks offer. Theological explanations posit a necessary being, God, who exists by nature and freely chose to create the universe. This shifts the question, but provides psychological satisfaction. Existence stems from will, from purpose, from a mind that decided something should exist rather than nothing. Critics point out this doesn't solve the fundamental mystery. It just relocates it to God's existence. Theists respond that God is fundamentally different from the universe, necessary rather than contingent, eternal rather than temporal, making God's existence more comprehensible as a brute fact than the universe's existence would be. Quantum cosmology offers a scientific-sounding alternative. Perhaps the universe emerged from quantum fluctuations in a pre-existing quantum field. The laws of quantum mechanics permit temporary violations of energy conservation, allowing particles to pop into existence briefly. Perhaps the entire universe is one such fluctuation that happened to last. But this requires quantum fields and their laws to already exist, which is itself a complex form of something rather than nothing. Quantum cosmology might explain how our particular universe arose, but it doesn't explain why quantum fields exist at all. The multiverse hypothesis we discussed earlier provides another angle. If all possible universes exist necessarily, if mathematical existence implies physical existence, then the question becomes, why is there something that can be described mathematically? This shifts the mystery to mathematics itself. Why does mathematics exist? Why does consistency exist? Why is there logic rather than illogic? These questions might be incoherent, asking for explanations beyond logic using logic, but they highlight that multiverse theory doesn't dissolve the fundamental mystery, it expands it. Perhaps the question itself is malformed. David Hume pointed out that our intuition demanding explanations comes from observing how things within the universe have causes, but it's a logical leap to assume the universe itself needs a cause. Causation might be a feature of processes within space-time, not applicable to space-time itself. Asking what caused the universe might be like asking what's north of the North Pole, a category error where the question doesn't match reality's structure. Let's consider a different angle, anthropic reasoning. We find ourselves in a universe with properties permitting our existence because we couldn't find ourselves in any other kind of universe. This doesn't explain why any universe exists, but it explains why this universe has observer-permitting properties. If countless universes exist with varying properties, we necessarily observe one capable of generating observers. Our existence selects from the ensemble of possibilities, explaining apparent fine-tuning without requiring design. Critics of anthropic reasoning argue it's unsatisfyingly tautological. We exist because we exist in a place that allows existence. But defenders counter that it's no more tautological than evolutionary biology explaining complex features through selection. Your eyes are well designed for seeing not because of teleological purpose, but because ancestors with better vision survived more often. Similarly, the universe appears designed for life not because it was designed, but because we observe one possibility among many that happens to permit observation. Still, even accepting anthropic reasoning in the multiverse, we're left wondering, why does the multiverse exist? Why is there a generative mechanism producing universes rather than absolute nothingness? Every framework bottoms out at a brute fact it cannot explain. For theism, it's God's necessary existence. For multiverse theory, it's the mathematical landscape's existence. For quantum cosmology, it's quantum field law's existence. Perhaps reality requires some unexplainable foundation, some ultimate brute fact that just is, without further explanation. The question, why does the universe exist, might be asking for a kind of answer that doesn't exist. We want satisfying, complete explanations because our minds seek patterns and reasons. But the ultimate ground of reality might not have a reason, it might just be. This isn't a failure of explanation. It might be reality's deepest truth. At some level, something must exist without further explanation, or we face infinite regress. Whether that foundational something is God, quantum fields, mathematical structures, or something else remains debatable. But its existence is unavoidable if anything is to exist at all. Now let's turn to meaning. Not cosmic meaning, but personal meaning. Does the universe's vast scale and potentially meaningless existence negate human meaning? Many people fear that cosmology threatens meaning by revealing humans as insignificant specks in an indifferent cosmos. If we're this small and the universe is this large, and if existence itself might be a purposeless accident, how can our lives matter? But meaning doesn't require cosmic significance. Meaning emerges from relationships, experiences, choices, and consciousness at human scales. The fact that you're tiny compared to galaxies doesn't make your experiences less real or your relationships less valuable. Vastness elsewhere doesn't diminish importance here. Your suffering still hurts. Your joy still delights. Your love still connects. The universe's size and indifference are irrelevant to these immediate experiences that constitute your life. Moreover, the absence of imposed cosmic purpose might be liberating rather than threatening. If the universe doesn't dictate meaning, you're free to create your own. Existentialist philosophers like Sartre argued that humans are condemned to be free. We must choose our values and create our meaning because no objective cosmic purpose constrains us. This responsibility is daunting but also empowering. You're not acting out a predetermined script. You're authoring your existence through choices and actions. Consider also that complexity, consciousness, and meaning might be what the universe naturally produces given time and appropriate conditions. The universe started simple, just energy, space, and fundamental fields. Over time, it created atoms, stars, planets, chemistry, and mind. Each step increased complexity and novelty. Perhaps the universe's purpose, if that word applies, is simply to generate increasing complexity and explore what forms matter and energy can take. You're part of that exploration, a configuration of matter that became capable of understanding matter. From this perspective, consciousness isn't an accident or mistake. It's an achievement, perhaps the universe's highest achievement so far. Unconscious matter organized itself through billions of years of cosmic and biological evolution into patterns capable of subjective experience and rational thought. That's extraordinary. And if consciousness occurs on Earth, it likely occurs elsewhere too, meaning the universe might be producing observers throughout space and time, each one a localized emergence of self-awareness from unconscious substrate. This view doesn't require believing consciousness is cosmically fundamental, or that the universe wants to create minds. It simply recognizes that physics permits complexity, complexity can become life, and life can become consciousness. These aren't violations of natural law. They're natural law's most interesting outcomes. You're not fighting against an indifferent universe to create meaning despite meaninglessness. You're an example of what the universe does when conditions allow. You're the universe becoming aware of itself through one particular configuration. Your consciousness connects you to every other conscious being, wherever and whenever they exist. You share the fundamental experience of being something that it's like something to be. A human, an alien intelligence, even a sufficiently complex AI, if consciousness exists there, they share with you the basic fact of subjective experience. This commonality spans whatever distances and differences exist between observers. In a universe mostly consisting of unconscious matter, consciousness is a rare and precious state, and every instance of it is remarkable. So what should you take from understanding cosmic scale? Perhaps these insights: first, humility. You're not the center of reality. Earth isn't special in cosmic terms. Human concerns don't dominate the universe's agenda. This recognition should inspire both ecological responsibility, care for the rare world you inhabit, and ethical consideration, recognition that other perspectives are as valid as yours. Second, wonder. The universe is far more magnificent than our ancestors imagined, and probably more magnificent than we currently imagine. Every expansion of knowledge reveals deeper mysteries. This should inspire curiosity, openness to new discoveries, and appreciation for reality's complexity. Third, connection. You're made of stellar material, governed by cosmic laws, embedded in universal space-time. You're not separate from the cosmos, observing it from outside. You're part of it, observing itself from within. This should inspire a sense of belonging to something larger than individual identity. Fourth, responsibility. You're among the rare configurations of matter capable of understanding and choice. This ability comes with responsibility to use it wisely, to create rather than destroy, to learn rather than remain ignorant, to cooperate rather than conflict, to preserve rather than squander. Fifth, appreciation. Your existence is statistically extraordinary. You occupy a special moment in cosmic time when stars shine and complexity flourishes. You possess consciousness, the universe's most remarkable known property. This should inspire gratitude for the improbable gift of awareness and, finally, freedom. The universe doesn't impose meaning. You create it through choices and relationships. This freedom is both terrifying and empowering. You're responsible for your life's meaning, but also free to choose what that meaning will be. The vast, indifferent cosmos provides a canvas on which you paint significance through how you live. The universe is bigger than we can measure, older than we can fully grasp, stranger than we typically imagine, and more mysterious than we'll ever completely understand. Within this vastness, you exist, a brief flash of consciousness experiencing reality from one particular perspective. This shouldn't make you feel meaningless. It should make you feel extraordinary. Against cosmic immensity, the fact that you're here, aware, thinking these thoughts, is perhaps the most remarkable fact of all. You are the universe understanding itself, and that understanding is itself a form of cosmic achievement. Throughout this journey, we've discovered that the universe's size transcends simple measurement. We've seen that the observable universe stretches 93 billion light-years across, containing 2 trillion galaxies, each with hundreds of billions of stars, but that this observable sphere is almost certainly a tiny fraction of reality's full extent. We've learned that cosmic expansion carries galaxies apart at speeds that can exceed light itself. Driven by mysterious dark energy that comprises most of the universe's content yet remains fundamentally unknown. We've explored how inflation transformed a subatomic scale region into something vastly larger in a fraction of a second, and how this process might continue eternally, creating infinite bubble universes beyond our reach. We've confronted the possibility that space extends infinitely, containing infinite copies of you living infinite variations of your life, separated by distances so vast that distance becomes an inadequate concept. We've contemplated multiverse scenarios where our universe is one among countless others, each with potentially different physical laws, scattered across dimensions of possibility we can barely imagine. We've measured cosmic distances using increasingly clever techniques, from parallax triangulation to standard candles to redshift relationships, building a cosmic distance ladder that extends from nearby stars to the edge of the observable universe. We've seen that distance in cosmology isn't simple. Objects can be farther away now than the distance their light has traveled to reach us, because space itself expands during that light's journey. We've learned that looking outward is looking backward, that every observation is historical, and that the present moment extends across space in ways that relativity makes fundamentally ambiguous. We've confronted the question of whether space is infinite or finite, recognizing that both possibilities carry profound implications we're still grappling with. We've accepted that absolute boundaries exist, cosmic horizons beyond which information can never reach us, black hole event horizons beyond which nothing escapes, quantum uncertainties that make some aspects of reality fundamentally unknowable. These boundaries aren't limitations of current technology. They're features of reality itself, mapped by our most successful theories. We've projected forward into incomprehensible futures where stars die, galaxies fade, black holes evaporate, and the universe reaches states so different from the present that our current cosmic era, the age of starlight, will seem like a brief opening chapter in a vastly longer story. We've accepted that everything familiar is temporary when viewed against cosmic time, yet found this doesn't negate meaning but contextualizes it within a universe that generates complexity wherever conditions allow. Perhaps the most profound insight is recognizing the relationship between vastness and consciousness. The universe needed to be roughly as large and old as it is for complexity like you to emerge. Stars required billions of years to forge heavy elements. Planets needed time to form and evolve life. Complexity demanded cosmic patience. The universe's vast scale isn't incidental to your existence, it's a prerequisite. A smaller, younger universe couldn't generate observers. So in a deep sense, the universe's size and your awareness are connected. The cosmos is big enough for consciousness to emerge, and consciousness emerges to understand that bigness. This creates a strange loop. Matter organizing itself into patterns capable of understanding matter, the universe developing structures that can comprehend the universe, physical processes generating entities that can describe those processes mathematically. You're not an outside observer examining reality from a privileged external position. You're part of reality examining itself from within. Your thoughts about cosmic scale are cosmic scale thinking about itself through the particular configuration that is you. As you go about your life after watching this, remember that every atom in your body has a cosmic history. The oxygen you breathe was forged in dying stars billions of years ago. The iron in your blood was created in supernova explosions. The hydrogen atoms in your water are primordial, formed in the Big Bang itself. You're not made of special biological substance separate from the cosmos. You're made of cosmic material temporarily assembled into a pattern called you. When you look up at the night sky, you're not seeing a separate realm disconnected from your life. You're seeing your origin. Those stars are your ancestors, the factories that created the elements your body requires. That darkness between stars is the expanding space that allowed those stars to form as separate entities rather than collapsing into one massive black hole. That faint light from distant galaxies is a message from the past, showing you how the universe looked billions of years ago. Every observation connects you to cosmic history. You are not a small thing lost in a large universe. You are the universe focused into one point of awareness, experiencing itself from one particular perspective, thinking thoughts that are themselves cosmic events. The neurons firing in your brain as you comprehend these ideas are matter and energy behaving according to physical law, yet generating subjective experience, the universe's most remarkable known property. This doesn't diminish you. It elevates you to your true status, temporary but essential, small but significant, part of something incomprehensibly vast, yet utterly unique in your particular existence. The question, how big is the universe, has no single simple answer. The observable universe has a measurable size, but the full universe might be infinitely larger. The inflated region from our Big Bang extends far beyond our horizon. Multiple universes might exist beyond any possible observation. And beneath all these spatial scales, there's the magnitude of mystery. Questions we haven't yet asked, phenomena we haven't discovered, aspects of reality we can't currently imagine. What lies beyond the observable universe? More space, more galaxies, more possibilities. What lies beyond that? Perhaps infinite continuation, perhaps other inflated bubbles, perhaps structures we lack concepts to describe. And beyond the multiverse? Perhaps mathematical existence itself, perhaps something entirely outside our frameworks, perhaps simply the groundless ground of being that requires no further explanation. If you made it this far, I deeply appreciate you taking this journey through cosmic immensity. Please subscribe and hit the thumbs up button. It genuinely helps others discover these profound truths about reality. And if you're hungry for more cosmic exploration, check out my video on the nature of time and whether the past still exists. I promise you'll find it equally mind-expanding. The link is in the description below. You are 13.8 billion years of cosmic evolution become conscious. You are stardust contemplating stars. You are the universe asking how big it is. And the answer, ultimately, is this. Big enough to contain you asking that question right now.